All right. So on this one, we are asked to find the sum of the roots. That means first things first is I need to find the roots of this thing. How do we find the roots of a quadratic like this? How do we find roots? Roots, also known as solutions, zeros, x-intercepts. How do I find those? Factor it. Those things all mean the same thing. Just putting all those words up there again. I know my handwriting's atrocious. So we're trying to take this thing and we're trying to factor it. I want to find my roots. So most of us tend to do like the x and box when we factor. Totally valid. There's quite a large number of options for factoring, and I don't care how you factor, just that you factor. I do need you to put some work on there. Don't just teleport unless you can explain it to me in detail. So when we're looking to fill in our x-frame to help us figure out what our pieces are, what goes here? What's in this spot? The a times c. So specifically, what is our a times c for this one? You say because the a is the guy in front of the x squared, right? So our 1 times our c, which is our minus 6. So we're going to have a minus 6 up here. And what goes on the bottom? Down here. The b. B's on the bottom. Okay, we'll start with b. That's how I remember that. So our b, which is the number in front of our x, which is just a 1. So what is a pair of numbers that multiplies to make negative 6 and adds to make 1? Because that's how we do this. Multiplies to be the top, adds to be the bottom. A pair of numbers that multiplies to make negative 6 and adds to make a positive 1. Yeah. We know that 3 and 2 multiply to make 6. If one of them's negative, we'll get a negative at the top, and that would give us a 1 on the bottom. Our difference is 1. And if I make the 2 be the negative, we're sure that our bottom's going to be positive 1. So what that gives us is how this middle term splits into 2 boxes. So we're going to have our x squared from the equation and our minus 6 from the equation. The only pieces that come out of the x box are the minus 2 with our middle variable x and our positive 3 with that middle variable x. So when we pull our factors, what do we get? So yeah, we're finding basically our greatest common factors, our GCFs, out of our columns and out of our rows. So what is shared between x squared and 3x? Just an x. What goes next to it? Negative 2. Good. On our rows, x and bottom row. I can't. It's going to be 3. Yep. So if I write this in factored form, I can write this quadratic as my x minus 2 and my x plus 3. So what are my roots? Because we were looking for those. This is factors. What are my roots? Yeah, that's when I take these guys and set them equal to 0. So this guy's going to give me a root of 2. This guy's going to give me a root of negative 3. And the question, because SAT people are weird, this is like the mathy part, and for normal, this is where we stop. SAT people are weird, so they want to know the sum of those two numbers. What do we do when we sum things? Add them. So for the SAT part of this, add 2 plus negative 3. Negative 1. Legitimately, the only reason we do this is so that on the SAT bubbles, you only have one circle to fill in. Legitimately, that's the only reason they have you do that. It's so stupid. Like surely there's a better way to do it. But that's the way they've figured out to make it so it's only one bubble. Ugh. Gross. For number 2 up here, we could either do this as an equation where I find my number, some number squared, and we know that the difference is 72, so I'd take my squared number and we'd subtract it. Like we could set this up as an equation with the difference. Or since it's multiple choice, we could just check these 4. When they give us options to pick from, see which ones fit. So we're looking here between a number and its square. So if this is my number, if 19 is my number, what is 19 squared? What is 19 squared? 361. What is the difference between 19 squared and 19? That means take 361 and find our difference. Difference means we subtract. What is 361 minus 19? 342. Is 342 72? Then we know it's not D. What do we think is probably our most likely option here? 9. Let's check that one and see if it fits. So we've got 9. If 9 is our number, and we're looking then at our 9 squared, a number and its square. What's 9 squared again? 81. What is the difference between the number and its square? So 81 difference with 9. What is 81 minus 9? 72. Ding, ding, ding. We have a winner. So our answer on this one would be A. So when they give you a list of options, you can absolutely write yourself an equation where I take a number and find the difference between it and its square to be equal to 72. You can write an equation. We could solve that. Set it equal to 0. Try and factor it. Doable, but gross. If they give you choices, test them. When in doubt, plug and chug. Take the numbers they give you and substitute them in, or think them through the problem. See if they make any sense. Okay. Questions on these two? Okay. Because we're going to be starting our next chapter today. Our next chapter is incredibly real-life relevant. Like, I know sometimes we do things that feel a little ridiculous. Like, why? What we do in this chapter is how credit cards work, how bank accounts work, how student loans work, how mortgages work, how the spread of infectious diseases works. Like, really, really relevant to real life kind of things. So this is the structure for it. So these are things, and it's probably a word you've heard before, are going to be called exponential functions. So we're going to be starting looking at exponential functions today. So we're going to look at some very, very simple ones today. And this is our very first form. This chapter, we're going to have a lot of different forms on our equations, just because as we get more and more detailed and closer to actual like banking equations, they're going to get a little messy looking. I'm going to walk us through them, but they're all going to start of this kind of basic form where we have that our function is a times b to the x. The difference between this and anything else we've done is x is not in the main section of numbers. X is my exponent. So what we're doing here is going to have a variable rate of change, is what it's called. When we think about things like lines, and we looked at how it was changing, it would be plus 3, plus 3, plus 3. It was always adding the same amount. It was that constant rate of change. Here we're doing a multiplying rate of change. So it's going to be like times 3, times 3, times 3 instead of plus. So our rate of change is going to be multiplying. Important pieces that we have here. This a that's out in front. So we have a times b to the x. A is going to be our starting place. It is always going to be our y-intercept. The initial value, it's where we start. I'm going to start with 3 rabbits or $1,000 or 200 guinea pigs. Like, we'll get a little sciencey in this chapter. But it's always going to be our starting amount. It is our y-intercept. It's where we start. The b, the piece that has the exponent on it, is what we're going to multiply by. So if it's multiplying by 2, a lot of times we'll say that it doubles. And so our base would be 2. If it's going to triple, it would be by 3. It's not always going to be that it grows, though. We'll talk about that in a little bit. But we're going to look at things in just a second. Let's talk about how we can tell whether it's going to get bigger or get smaller. But our starting place is our y-intercept, and that's our a. And our multiplying, or how it's changing, that's our base, that b that has the exponent on it. And we're going to start by looking at a couple of tables so that we can see how we can tell what's happening, what it looks like if we're looking at a table, kind of a little bit of it. So since we're going to look at a couple of tables, and I don't want us to spend a ton of time writing down tables, I made copies of them. I also have on here a couple of problems we're going to look at today. So I'm going to pass these out. Like, we're going to go in this order, except for this one, we're going to do that order. So I'm going to pass these out so you have them. Just again, I try and make it so it's not that we're racing paragraphs to write things down. I'd rather us have time to think rather than trying to rush write a table or a sentence or things like that. Sometimes I do make you write things down, and these are important enough that I need you to write them. Because there have been studies that writing things down does help you to remember them better. So we will hopefully get through everything on here. We may catch the Albany one tomorrow. But we'll see. We'll see how it goes. So what we're going to start with is we're going to look at these two tables, and we want to see which of these is an exponential function. So we're going to look at these two tables. I'm going to start by looking at the left-hand one, and we're going to see if we can figure out what kind of function it is. And the way we do that when we're looking at functions is we usually look at kind of the same way of looking to try and find slope. We can see what's adding in our x's, what's adding in our y's. So if I look at my x's over here, I know going from 1 to 2, we're going to add 1. To go from 2 to 3, we add 1. To go from 3 to 4, we add 1. So our x's here are changing in a very consistent rate. That is always really important when we're looking at slope. Those should always be consistent, meaning the same. What happens to our y's on this first table? How did we get from 5 to 12? 5 plus what gives us 12? 7. So we added 7 here. 12 plus what gives us 19? What's going to be on this next one? 12 plus what gives us 19? That one's going to be another 7. 19 plus what gives us 26? 7. And 26 plus what gives us 33? 7. So what kind of function is this? If my rate of change, how it's changing here, is exactly the same on this first set, what's this going to look like if I was to sketch it out and graph it? Well, I'd have my 1, 5, my 2, 12, 3, 19, 4, 26, 5, 33. What shape is this making? A line. When our rate of change is consistent or constant, this is not changing. We have a linear function. This is a line. So let's see what's different about the one over here on the right. My x's are still changing in a very similar way. My x, to get from 0 to 1, we had a +1. I don't like that being right there. I want it inside. There we go. +1. To get from 1 to 2, again, we add 1. To get from 2 to 3, we add 1. To get from 3 to 4, we add 1. I took the easy one on here. What's happening to my y's? 15 plus what gets me to 75? Plus 60. 75 plus what gets me 375? 300. 375 plus what gives me 1875? 1,500. One more. 1875 to 9375. There we go. I'm good at reading. Say it again. Not 8,000. Close though. It's going to be 7,000. 7,500. So, easy question here. Is this a line? It would need to add by the exact same amount. What do we notice is happening with these numbers here? What do we notice between 60 and 300, 300 and 1,500, 1,500 and 7,500? What do we notice about those? Or what if I do it and take off? What about that? If I just look at it as 6 and 30 and 150. What do we notice about those?
It's multiplying by 5.
They're multiplying by 5. Even if I put those zeros back, to get from 60 to 300, we multiply by 5. To get to 300, to get from 300 to 150, 1,500, I'm good at words, it would be multiplying by 5. And even in here, 15 to 75, that's times 5. This guy is times 5. This guy is times 5. This relationship is times 5. Everything has been times 5. It's not an adding change, it's a multiplying. So that means this is going to be an exponential function. Exponentials change by multiplying. And what that would look like if I was to kind of sketch this guy out, same way I did for the other graph, we have our 0, 15. I'm going to make our scale very, very small. 0, 15. And I've got 175, 2, 375, 318. We're way up here. 4, I'm going to go with that's about on the ceiling. So this graph, if I was to sketch this out, looks kind of like this. We will get more into details of graphing way later on, but just kind of to get the visual of what this is. It's going to go real, real slow, and then it's going to go and take off like a rocket. Okay, so that's kind of the vibe of what these look like. And that's how we can tell by looking at a table what's happening here. We're looking for these pieces that are multiplying. So we're going to have a couple of different ways of marking things down. What we're going to look at next is we're going to look at some equations because we have two technically different kinds of exponential functions. We could have something like this where it's growing and getting bigger and bigger and bigger. Or I could take numbers and I could see if I could make them smaller and smaller and smaller. What that's called is called decay. And we're going to look here on how to figure out whether something is growing or something is decaying. Remember, every single time it changes by multiplying. So what would we be multiplying something by if I want to make it be smaller? How can I multiply something and make it smaller at the same time? Negatives, it does make it smaller, but only temporarily because then it'll switch it back. So not negative, not what I'm thinking. Number smaller than 1. If I took a decimal or a fraction, think about 0.5. If I took 4 times 0.5, it would get smaller. If I take 4 times 1/2, it gets smaller. So if we have decimals that are less than 1, or if we have fractions that are, small, that's when we're going to have decay. So these two pieces, growth or decay, are both looking at our base. So our A, our where we start, is out in front. Our base is what we're looking at here. So if our base is small, it's going to be decay. If our base is bigger than 1, it's going to be growth. So what we're going to do is we're going to look at these pieces. We're going to figure out what our A is, we're going to figure out what our B is, and we're going to decide if it's growth or decay. That is what we're doing with these problems here. So looking at 3 to the x here. What is my base? What is my B? The base is the piece that has the exponent. So sometimes it'll have parentheses. So our base here is 3. So what's my A on it? What's my starting value? Not 0, because it's multiplied. I think I heard it.
1.
1. I was going to say, I heard it. It was quiet, but it was there. I could put a times 1 out front.
That isn't. I was going to say that was the multiply.
I missed the last word on that, so I have no idea what you said.
Symbol.
Simple. Okay, yeah. Yeah. So there's that kind of invisible 1 that's in front of things. That 1 is there. So if my base is 3, that means it's going to times by 3 every time. So is this going to get bigger or is this going to get smaller? Is this going to be growth or is this going to be decay? If my base is greater than 1, it's going to be growth. Since my base is 3, this is going to get bigger. This is going to be growth. If my base is less than 1, that's when we have decay. We will never have negatives inside because it's mathematically gross, and it looks absolutely terrifying when you graph it. So we won't have negatives inside there. Let's look at our next one over here so we can practice identifying these pieces, because these pieces are like super important with what we're going to work with. So what is our base on this one? 1/2. What is our A on this one? What is our leading coefficient? 1. Again, this one doesn't have a number written out in front, so the only thing we can times by and not change it is 1. If we put a 0 out there, it would make this whole thing 0, and then it's no longer a thing. So since my base is 1/2, is this function growth or decay? Decay, because it is a small number. So then they're going to get a little bit more busy over here. Same vibe, though. We're going to find what's our base. We're going to find our starting amount. So our B and our A. What is my base on this one? 1/3. What's my A? My starting amount? 5. Our initial value. So is this one growth or decay? It is decay. It is the base that makes the choice. So this is decay. So what this one would be, it'd be something that I start with $5 and I'm losing a third of it in fees every year or whatever. 2 more, one of which is normal, the last one's trying to show us a thing. So what is our base on this next one? 5. And our initial value, our A, is 1/2. So is this one growth or decay? Growth. On all of these ones that we've looked at, they've had one thing that's the same that's different on the last one. These are all to the power of x. Questions on these 4 before we look at the last one, which is showing us a thing. Okay. On this last one, we have 2 to the minus x. So our first instinct would be to say that our base is 2, right? But on all the other ones, it had just an x as the exponent. So I really can't judge it right now because I don't have just x. I have minus x up there. So what I'm going to do is I'm going to use some of my old school Algebra 1 like exponent rules to fix it because I don't like that. So I could rewrite, just like back in when we did our square roots and we were looking at those negative square roots, and I factored out a -1, where I put my -1 times x. We can write it like that. It means the same thing. And then if we think back to our old school algebra rules, and we remember that when I take exponents and I multiply them together, that is the same thing as if I take my 2 to the -1 and we raise it to the power of x. Those things all mean the same thing. I'm going to write it in one more different way. Because what does a power of -1 do? We just look just inside here. What does 2 to the -1 look like? If you type 2 to the -1 in the calculator, what do you get? Type it in. 2 to the power of -1. 1/2. So what does a negative exponent do? It gives us the reciprocal. So 2 to the -1 is the same thing as 1/2. So this thing is really the same as 1/2 to the x. So 2 to the -x is the same thing as 1/2 to the x. So is this growth or decay? This is decay. We're not going to see it tons where we give you negatives in the exponent like this, but it is going to be important for us to be able to recognize this and write it like that. So if we have a negative in the exponent, we got to watch out for that because it's really actually telling us to look at the reciprocal. So, questions on this as it sits right now? Because I know that in our head right now we're going, why? We're going to do our very first one. So here's our first problem that's underneath, and we're going to see what this is about. So if we think about our function, our initial function, where we have our f of x, which is, again, y, is our a times b to the x. Remembering that a is our starting amount and b is our how it changes. We've got here that the number of fruit flies in an experiment doubles every hour. And we're starting with 25 fruit flies. What does it mean for something to double? Times 2. Times 2. So what that's telling us is that's telling us how it's changing. It's telling us what is changing for each x. So that's going to tell us our base. So this guy is going to be our b. So when we come to write an equation, our b is going to be that 2. It's doubling. 2 to the x. We're going to have x as our exponent. What's our a going to be? That's what we start with. We start with our 25 fruit flies. So our equation for our how many fruit flies are there, we can write it as y equals 25 times 2 to the x. So at the start of the, I'm just going to fill in a couple values here. At the start of our experiment, right at time 0, we're going to have 25 fruit flies, right? That's what they tell us. After 1 hour, how many fruit flies are we going to have? If they double every hour, we're going to have 50. How many would we have at 2 hours? Careful, careful. It's going to double. How do I double 50? We get up to 100. If I go another hour, how many are we going to have? 200. Because these are going to go times 2, times 2, times 2. So we'd have 200. So they're growing a lot, really fast. So if I want to know how many there's going to be after 1 day, how are we going to figure that out? I don't want to have to keep going and fill in the whole table because remember, these are counting by hours. Hours. Because how many hours would I need to do? How many hours make a day? 24. So instead of me having to fill this table out all the way down to 24, what could I do with the 24? Put it in for x. So we could take and type into the calculator our 25 times 2 to the 24 power. And I'm going to grab my calculator and do that for us so we can see it. I have to turn this off. Oh, and my foot is asleep. There we go. So I could straight up do my 25 times 2 to raise it to our power. Anything that's not a 2, we use that button right there. And I can put my 24 in. And how many fruit flies are we going to get? A lot. We get 419,430,400. That's why we want to get rid of the fruit flies the very second we see them. There was your life pen. Oh, that's a lot. Okay. So 24 hours in this experiment, we'd have our 419,430,000. 400? Did I remember it right? Oh, look at that. Flies. And that's why you see a lot of times science experiments that use things like fruit flies is I could do several generations in the span of a couple of days. And also why your grown-ups get real mad when you start leaving food out that attracts flies is they multiply real fast. Okay, so we're going to be working with things like this. Sometimes we're going to be growing and getting really big numbers. Sometimes things will get small. Sometimes things are going to get decimally. I have one more bit I want us to look at today, and it's actually the graph thingy at the very, very bottom of our page. We'll do our Albany, Kentucky problem tomorrow, just because we don't have a ton of time. So I'm going to look at these two graphs because I want us to see a thing here since we've already been talking about it. I've got two graphs up here. I've got a red one and a blue one. I know they're shaped, they're very, very similar on the copies, but I didn't have time to edit it. And I want us to look at the two things. Our two graphs up here. They're very, very similar. What do we notice about them? Which one might be growth, do we think? Red or blue? Red. Red is definitely, this one is growth. This is our, we're going to call this one f of x. Is growth. So the blue one is probably going to be representing what? Decay. That's what decay graphs are going to look like. What is the difference here? What do we notice that's the same about our growth equation and our decay equation? What do we notice is the same? What do we notice it's different? Because they're real similar, right? They're very much similar, very much like how we would take our parabolas and reflect them this way. Where we'd make them go upside down when we reflect it over our x-axis. What does it look like we did with our red graph here to make the blue graph? I take my red graph. Yeah, we're headed that direction, absolutely. Yeah, you're headed right there. This one did a reflection, but instead of going upside down across the x-axis, this one spun and it went the other way. So we went from growth to decay like this. So what this is called is this is actually a reflection over the y-axis. We're going to start to see that. That's why we've been so specific about reflecting over the x. This is a reflection over the y. So what we want to look at, our last bit we're going to look at today is a possible equation for each of these things. So think through the pieces we use in our equations when we have our starting amount, what it multiplies to change, and then we have our x. So looking at red, we're just going to look at red. Where is our starting amount? What is our y-intercept? 1. And in fact, they both have that same y-intercept. So we know for a fact our y-intercept is 1. That's our a. To figure out how it's changing, I'm going to look at the next couple of points. If I look at this guy, this guy, this guy. If I start at 1, what do I need to multiply it by to get to 2? 1 times what is 2? 1 times 2. 2 times what gives me 4? 2. 4 times what gives me 8? 2. So this one is doubling every time. It's multiplying by 2. So I could write the equation for my red line as 2 to the x. Every time it goes up by 1x, it times by 2. So how do I take that from a growth equation and make it be a decay equation? How do I take it and switch it? It's exactly what we're going to, so it's not quite the inverse, but I was like, I see what we're thinking. It's actually this guy right here. It's related to my 2 to the x. Like that's what we had. We had 2 to the x. That's this guy. It's super duper related. It has that same starting amount. It's still changing by the same amount because everything's just reflected. It's just that it's decay. So I have a couple of different ways I can write it. I can write it as my 2 to the minus x, or I can write it as my fraction. So I have 2 different equations I can write for blue, and that's going to be our 2 to the minus x. That's what gives us our reflection across our y-axis, or I can put this as our 1/2 to the x. Either way, those both mean the same thing. So we are going to keep working with these exponential functions tomorrow. Tomorrow we'll get into that last problem that was on there for Albany, Kentucky, and we'll start looking at our rates of change that are a little bit different. I have the first homework for you. There's honestly not a ton on here from what we did today. It has a little bit of the graph stuff on the back and a little bit of identified, which are growth and decay. We will get through, for sure, the story problems on the front tomorrow. Hopefully we get through a little bit of what's on the back, but honestly, I don't know. We really don't. When I get through what we get through. But, so this is for sure not gonna be due until at the earliest Monday, because we need to talk about the front yet. Alright, so I'm giving it to you, but there's, again, not tons that you can do on it, but that way we can have it. So we're gonna start working with all these things that are on the front tomorrow, on what's growing, what's getting smaller, all that jazz. Okay, so our chapter test for this chapter is, I believe, March 13th, 14th, I think 13th. I think I didn't update that one. Nope, that one says 14th too. I think it might be on the 14th. I will double check. That's called, I have been so busy this week, I forgot to look at the actual calendar. March 14th is correct. March 14th is when we're having our chapter test. Okay? Yes, dear.